Hello everybody, this is about Chapter 7, Gravitation. We go to overview for Chapter Gravitation. We have three main subtopics. 7.1 is about gravitational force and field strength. In this subtopic, we learn about Newton's law of gravitation. Formula for Newton's law of gravitation is F equal to G mm over r square. In this subtopic also, we will learn about gravitational field strength. Formula is Ag equal to Gm over r square. For subtopic 7.2, gravitational potential energy means the work done by a gravitational force in bringing a test mass from infinity to a point. Formula is U equal to negative Gmm over r. For subtopic 7.3 is satellite motion. In this subtopic, we will learn escape velocity, we will learn linear velocity or tangential velocity, and we will learn orbital period. We go to gravitational force and field strength. Newton's law of gravitation states that a magnitude of an attractive force between 2 point masses is directly proportional to the product of their masses and inversely proportional to the square of the distance between them, or F directly proportional to the product of mass, meaning that if product of mass increase, gravitational force will be increased, and F inversely proportional to the square of distance. If square of distance increase, gravitational force will be decreased. Or mathematically, you'll get F equal to Gmm over r square. Okay, F is gravitational force, mm is masses of particle 1 and 2, r is distance between particle 1 and 2, G is universal gravitational constant 6.67 times 10 power of negative 11 Newton meter square per kilogram square. Okay, this is illustration of Newton's law of gravitation. Okay, if we have two mass, two particle or two object, so each particle must have their own mass m1 and m2. Okay, between these two particles, we will produce attraction force. Okay, F21 and F12. These attraction forces we call as gravitational forces. Value for F21 equal F12, but in opposite direction. We go to example 1. Determine the distance of spaceship from the Earth at which the gravitational force due to the Earth twice the magnitude of the gravitational force due to the Moon. Okay, so given mass of Earth is 6 times 10 power of 24 kilogram, mass of Moon is 7.35 times 10 power 22 kilogram, mass for spaceship is 9,000 kilogram, and distance between Earth and Moon 3.84 times 10 power of 8 meter. Okay, this is illustration. Between Earth and Moon, we have spaceship. Okay, so the question asks the distance of spaceship. Okay, the distance of spaceship, okay, we symbol as x. Alright, so the distance between Earth and Moon is r Earth Moon. So the balance length between spaceship and Moon is r Earth Moon minus x. The key word here is force due to the Earth twice the magnitude force due to the Moon. So force due to Earth's spaceship is twice force due to spaceship moon. Okay, so we replace this concept with the formula. Formula for first Earth spaceship equal G mass Earth mass spaceship over x square equal to 2 G mass moon mass spaceship over R Earth moon minus x square. Then when we substitute the value was given, you get the answer. The distance between Earth and spaceship, okay, equal to x is 3.32 times 10 power of 8 meter. Alright. We goes to next subtopic 7.12 is about gravitational field. Gravitational field is a region of space surrounding a body that has the property of mass where the attractive force is experienced if a test mass placed in the region. For spherical objects such as the Earth, the field is radial. Okay, so let's say this one is Earth. So, surrounding of the Earth is gravitational field in radial. The gravitational field in small region near the Earth's surface are uniform and can be drawn parallel to each other. Let's say below is Earth's surface, so the direction of gravitational field is towards downward. Alright? We goes to gravitational field strength formula. Okay? What is gravitational field strength? Gravitational field strength is gravitational force per unit mass of a body placed at a point. Or, look at this formula, Ag equal to F over m. Okay, this equation is come out from F equal to ma. So when we arrange A in front, so you'll get A equal to F over m. F is gravitational force, Ag is gravitational field strength, m is mass of a body. Or A equal to Gm over R square. G is gravitational constant, m is mass of point mass, r is distance between test mass and point mass. For gravitational field strength is a vector quantity. Unit is Newton per kilogram or meter per square or meter as negative 2. It also known as gravitational acceleration in free fall acceleration. Its direction is the same direction of gravitational force. We go to example 7.3. Determine the Earth's gravitational field strength A on the surface. Given value G equal to 6.67 times 10 power negative 11 Newton meter square per kilogram square. Given mass of Earth 6 times 10 power 24 kilogram. Radius of Earth 6.4 times 10 power of 6 meter. And then we use equation G equal to Gm over R square. So because of the question asked on the Earth's surface, value of R will be R equal to radius of Earth. So the value radius of Earth was given here. So we just substitute value G times m, mass of Earth, over R square. And then you will get the answer, gravitational field strength equal to 9.77 meter as negative 2 toward to the center of Earth. For the question B, determine the Earth gravitational field strength on altitude 350 kilometer. Okay, so for this question, we need to find R. r is a distance between Earth's center to that point. So now the question given is altitude. Altitude meaning that the height from Earth's surface to this point P. H. 350 kilometer only for height from Earth's surface. So how to determine the r? R is a distance between Earth's center. So r equal to radius of Earth plus altitude or height. So we get the value for r is 6.75 times 10 power of 6 meter. Then we use equation gravitational field strength A equal to gm over r square. G is constant value 6.67 times 10 power negative 11. M is mass of Earth 6 times 10 power of 24 divided by r square. R mass distance from center of Earth to that point. So value of r here is 6.75 times 10 power of 6 squared. So the value of A equal to 8.78 meter per second square. The direction is towards the center of Earth. Okay, for subtopic 7.2 is about gravitational potential energy U. Okay, what is U? Is defined as the work done by a gravitational force in bringing a test mass from infinity to a point. Let's say this point P at infinity. This one is Earth. So surrounding is Earth, we have gravitational acceleration, okay, or gravitational field. Okay, so the work done to bring in a test mass P to the Earth, work done, we call as gravitational potential energy. So formula for gravitational potential energy U equal to negative gmm over r. Okay, and then gravitational potential energy is a scalar. Alright. So the change in gravitational potential energy delta U equal to U final minus U initial, or mathematically U final equal to negative gmm over R2. R2 is position at final minus negative gmm over R1. R1 is position for initial. If we rearrange equation, we'll get delta U equal to gmm bracket 1 over R1 minus 1 over R2. The variation of gravitational potential energy U when the test mass M move away from the Earth's surface, okay, is illustrated by this graph. Okay, from this equation, U equal to negative gmm over R. Okay, so look at the relationship between U and R. So you'll get U is inversely proportional to the R. When R increase, value for U will be decrease. So from this graph, look at the value. If R increase, value for U is approach to 0. Okay, and then the gravitational potential energy at infinity is 0. We go to question. The moon has a mass 7.35 times 10 power of 22 kilogram and radius 1740 kilometer. A probe of mass 100 kilogram is dropped from a height 1 kilometer onto the moon's surface. Calculate its change in gravitational potential energy. So the question asks delta U. Alright, we go to the solution. This is given value, mass of moon, radius of moon, mass of probe, and distance R2. Okay, so distance R2 here is 1.71. Value for R2 equal to R, radius of moon. Why? Because at final position, this probe is dropped onto moon surface. Okay, look at this picture. At initial position, this spot is 1 times 10 power of 3 meter from moon surface. And then this probe is dropped onto moon surface. So the final position at moon surface. So R final equal to radius of moon. Okay, now we need to find R initial. Also R1. R1 equal to radius of moon plus altitude equal to 1.741 times 10 power of 6 meter. So, the change of gravitational potential energy delta U equal to U final minus U initial. Okay, or we directly use this formula. G(m)(m) 1 over R initial minus 1 over R final. Okay, so value for G is gravitational constant was given. M is mass of moon, capital M, and then M, small m is mass for probe. Okay, and then R initial is 1.741 times 10 power of 6. R final, because it dropped on moon surface, so R final will become radius of moon, 1.74 times 10 power of 6. So delta U equal to negative 1.62 times 10 power of 5 joule. Alright? Okay, we go to last subtopic 7.3, satellite motion in a circular orbit. 7.3.1 is escape velocity. What does it mean, escape velocity? Is minimum velocity required by a mass to escape completely from gravitational field to infinity in outer space. Okay, look at this picture. Okay, this rocket want to escape completely from Earth gravitational field. So this rocket need high velocity to escape completely. What happen if velocity rocket less than escape velocity? Yes, the rocket will be fall downward back to the Earth surface. Right. So formula for escape velocity equal to sub 2gm over r. Remember, m here is mass of Earth, not mass of rocket. R is a distance between the test mass and the Earth's center. If the test mass of Earth's surface, distance r equal to radius of Earth. So formula escape velocity equal to sub 2g r. R is radius of Earth. Look at the example 7.9. Question A. Calculate the escape speed from the Earth's surface for a rocket of mass 300 kg. Okay, so Earth's surface here is R. So R equal to radius of Earth because this rocket on Earth's surface. So we use formula. Look at this solution. Formula V escape equal to sub 2gm over r. And then r here equal to radius of Earth. So substitute value. Remember, m here is mass of Earth, not mass of rocket. Don't confuse it. So substitute the value. Velocity escape equal to 1.12 times 10 power of 4 meter per second. Question B. Kinetic energy of the rocket in order to move infinitely far away from the Earth. So using equation, kinetic energy equal to half mv square. But v here we replace with escape velocity. Then we use escape velocity value at part A, substitute here. And then you will get the answer, kinetic energy equal to 1.88 times 10 power of 11 joule. Next, we go to tangential or linear or orbital velocity. Okay, what does it mean, tangential or linear velocity? Look at here. A satellite of mass m traveling around the Earth mass. Okay, this one is satellite. Okay, and then traveling around the Earth in circular orbit. Okay, so this satellite keep moving in circular orbit. Why? Yes, because it have two forces attract this satellite toward to the Earth. Okay, this forces is Fg, gravitational force. At the same time, we have Fc. Fc is centripetal force. So, Fg equal to Fc. Gravitational force equal to centripetal force. That's why this satellite keep moving, traveling around the Earth. Okay? What happened if no more gravitational force? What happened to the satellite? Yes, look at here. Satellite will escape from orbital radius. So this satellite will move at tangential velocity. So you need to derive tangential velocity by using this concept, Fg equal to Fc. So when we substitute with formula, Fg equal to gmm over r square, Fc equal to mv square over r. Then we rearrange the equation, v equal to surd gm over r. Mass here is mass of Earth, not mass of satellite. Alright? So remember, v is velocity of satellite or tangential velocity. R is a distance of satellite from the center of the Earth. Mass is the mass of Earth. G is universal gravitational constant. Okay? For satellite close to the Earth's surface, meaning that R is a distance equal to radius of Earth. Therefore, as velocity linear equal to surd g r, r for radius of Earth. Alright. Since v equal to r omega equal to 2 pi r over t, so we substitute, we get 2 pi r over t equal to surd gm over r. And then we rearrange equation, we will get the period of satellite orbits around the Earth is t equal to 2 pi surd r cubed over gm. For subtopic 7.3.3, synchronous or geostationary satellite. Okay, the satellite have the following characteristic. What is geostationary satellite? First, it revolves in the same direction as the Earth. Number 2, it rotates with the same period of rotation as that of the Earth, 24 hours. Number 3, it moves directly above the equator. Number 4, the center of synchronous satellite orbit is the center of the Earth. It is used as communication satellite. We go to example 7.12. The radius of moon orbit around the Earth is r, and the period of orbit is 27.3 days. The masses of Earth and Moon are 6 times 10 power of 24 and 7.4 times 10 power of 22 kilogram. Calculate the radius of the Moon orbit. Alright, so this one is Earth, this one is Moon. So calculate the r by using formula period t equal to 2 pi times surd r cubed over gm. So now t was given is 27.3 days. You need to change to second first. So t equal to 2.36 times 10 power of 6 seconds. Alright. So g is gravitational constant. Mass here we refer to the mass of Earth. And then not mass of Moon, mass for Earth. Alright. So when we substitute the value, you get the answer R equal to 3.84 times 10 power of 8 meter. Okay, thank you.